Hi, so today we'll be discussing the paper An Image is Worth One Word, Personalizing Text to Image Generation using Textual Inversion. This is usually called Textual Inversion, and this is most likely a word play on An Image is Worth 16 cross 16 words, which was the Vision Transformer paper, which divided a image into 16 cross 16 grid to extract embeddings from it. Anyway, it is by Rinon, Yuval, or Amit, Gal, and Daniel from Tel Aviv University and NVIDIA. So, what is it about? Uh, TLDR, it is about fine-tuning diffusion models or like personalizing diffusion models to uh, generate images of a new concept. So, first, what are diffusion models? For the purpose of this paper, I'm not going very deep into them, but essentially diffusion models allow you to are a sort of generative model which allow you to create images, audio, or whatever. In this case, we'll be focusing on image. So more specifically, they are focusing on text to image models, which case you give it a text and it gives out an image. So in this case, an oil painting of a star gives you an oil painting of a star. What is a star? We'll come to that next. So diffusion models are great. Text to image models are great. They give us a lot of good results. As they say, they offer unprecedented freedom to guide creation through natural language. But what if you want to teach your model a specific concept? Like you've trained a big model, but now you want to train it to generate an images of your cat. Like you want to say, how would my cat look like a Beethoven, oh sorry, Beethoven, not Beethoven, Van Gogh painting, or what, how you want to imagine a new product based on your favorite toy. So in this cases, you want to teach a new concept to your model. You want the concept could be how does your cat look like, or how does your favorite toy look like, and then you want to be able to use those new concepts with your text prompting to generate new variations of those, like to use those concepts in new settings. So what they present is that using only 3 to 5 images of a user provided concept like an object or a style, they learn to represent it using new words in the embedding space, and these words can basically be used like any other word. So what they mean is that uh, you see this example. Say you provide these 4 photos of a statue. What it will do is that it will somehow learn a new word star which represents this statue. And then this star is like any other word in your vocabulary, and you can use it in natural language. So you can say an oil painting of star. So the model will understand that it needs to create an oil painting of this statue, or something like this statue, or an app icon of a star. So a star is just like any other word. So if it was like a dog, an oil painting of a dog, it would have created an oil painting of a dog. It has just learned a new word, a star, which represents uh, this statue, or in this case, this cat. So it learned that this star represents this cat, and then it is even able to like create 2 cats. You just say, I need 2 star fishing on a boat, so it will create 2 star, like 2 cats. So essentially, you teach the model a new word for your concept, and a word is nothing but an embedding in this case. So because this model use so the way text conditioning works is that these text prompts are like passed through a BERT model or any some sort of transform model, and it creates an embedding for each of these, and then I think averages out those embeddings. So we'll essentially learn a new embedding which will represent this new concept. So yeah. So here they go into a bit more motivation for their particular approach. So what they say is that introducing new concepts into large models is like difficult. So they say that if you like retrain a model for each new concept, it is very expensive. You can't possibly imagine to retrain your entire huge model for each new concept you want. And also at the same time, they're saying that fine tuning on a few examples leads to catastrophic forgetting. So what they mean is that you had a model and you fine tuned it on some new concepts, say like the concept of your cat. If you do it naively, the model might forget its previous knowledge. Like it might forget, say, how a dog looks like, or like uh, the other things it was trained on. It might forget if you are fine tuning it to focus on a new concept. And they say that there are some approaches which freeze the original model and instead like train new adapters on top of it for new concepts. So, like you might have your old model, which is your big model, and you freeze it. This is like freezed. Freeze. So its weights are not changing, and for each new concept, you might learn a new adapter model on top of it. So this might be representing a cat, or this might be another one might be representing a dog, or something like that. And you just plug these together as and when needed for each of your concept. But again, they say that this approach is prone to forgetting prior knowledge, or it might be hard for the model to access these concepts uh, along with the prior knowledge. So what this means is that when you do this sort of adaptive thing, like adapter thing, you add this new model for a cat. It might work well enough for a cat, but if you want to uh, like access some old knowledge, like say the model previously knew how to generate oil paintings. So it might not be able to combine that old knowledge of generating oil paintings with the new knowledge of generating a cat. So that is something they say. I I do think that they are alluding to this adapter approach is sort of like low rank adaptation of language models, which divides the weights into two parts, a fixed part and a fine-tuned part. But yeah, whatever. So what they propose is that let's not touch the model. Let's keep the model as it is. We'll instead find new words in the embedding space to represent our concept. So the goal is to find new embedding vectors that represent new specific concept. So we learn a new pseudo word represented by a star, and that word is like treated as any other word, and it can be used to compose new queries and whatever. So you can therefore ask for a photograph of Esther on a beach, or an oil painting of Esther hanging on a wall, or even compose two concepts like a drawing of S1 star in the style of S2 star. So S1 star is one concept you taught and S2 star is another concept you taught, and you can like even learn to merge them together because they are just like any other word. So the main reason why this works is because you are leaving the generative model untouched, right? So you are leaving the model untouched. You had this huge model, big model, and you were giving it text input, like you were giving it T1, T2, T3, and whatever. So you are you're not changing anything in the model. Nothing is being changed here. You're just learning a new word. So the capabilities of the model are the same. You're just learning a new word embedding to access a new concept. There then lies a problem I have with this approach because we are not changing the model. It means that it can't learn new things. So if you want to teach a new concept which is like totally out of distribution from the original uh, data set it was trained on, this can't work because it has no way of accessing new knowledge. By learning a new embedding, you are essentially just uh, accessing the knowledge which was already there in the model. So you can think of it something like that. This model has a lot of information, and the text is how you access that information. So the model knows how to create a lot of images, and the prompt is how you access those knowledge. And learning new words is just like unlocking new areas of that existing knowledge. However, you can't expand the knowledge. So if the model was trained on a data set of dogs, you can't create a data set of cats using this approach, even if you provide it like other uh, like images of a cat, because that model is not trained to generate images of a cat. So this is, I think, a drawback of like freezing this model. But yeah, the save here is that these models are usually trained on such a huge data set and such a diverse data set that they practically cover almost everything. So you can actually focus more on just accessing the knowledge of the model instead of like trying to fine tune the model. This is also similar to ChatGPT and stuff. They have a lot of knowledge. You just have to learn how to access those knowledge using new prompts. So yeah. So they say that they frame this task as one of inversion. Inversion basically means here is that our model is fixed. So we have a fixed pre-trained text to image model and a few images depicting the concept. We have to find this new embedding, this new S star. So we are not changing the model. We are instead inverting this model to find the input which will give us a necessary output. So inversion is like you have X, you have a function, and you have Y. Inversion is learning that what is the X which will give me a particular Y. So you are finding X instead of like changing F, you are finding X that will lead to a particular Y. So in this case, we have a bunch of images which we want to produce, and we have a function which is a model. We want to invert and find out what input embedding or what input token we should give it to generate those images. All right. And this inversion approach is sort of popular in GANs. So uh, in GANs, people try to learn latents, which will lead to a particular image by inverting to find that latent. So yeah, they draw some parallels on top of it. Yeah. So here they talk a bit more about inversion. So say that manipulating images with GANs often require, sorry, generative networks often require one to find a corresponding latent representation of the current image. This is known as inversion. So as I said before, uh, for a GAN, say a GAN, you have a GAN. So okay, you have a input latent and you get an image out of it. It outputs an image. So inversion is finding out this latent, which will give a particular image. So you want an image of a person, you will find a latent which gives the image of a person when passed through a model, say a GAN. So there are two ways of doing it. One is optimization based and another is encoder based. In optimization based techniques, you directly optimize this latent vector such that feeding it through this GAN would recreate the target image. And in encoder based approaches, you have a separate model which will like predict this latent. So encoders leverage a large image set to train a network that maps images to their latent representations. So uh, you might learn an encoder which will encode this into that latent space. So you might be thinking, why do we want to do this inversion? Well, if you have the latent of a image, then you can modify that latent to uh, do some cool things. So like if you have a separate image of a cat and you find it's latent, and you have the latent of a person, then you can like fuse these two latents, like interpolate between them to get some hybrid of these things. So extracting the latent a latent is something which you can play around with and pass with the model to generate new types of uh, image fusions, and you can even do image editing by changing the latent in a smart way, something like that. So they say that while the above works invert a given image into the latent space, they want to invert a concept. So instead of like inverting a single image of a person into a latent, they want to embed the concept of a person, like what a person, like how to represent a person into a latent, and they use that embedding vector for that. Okay, so now coming to the method. So essentially we have to find out this new embedding which will represent the concept. And they say that some approaches, previous approaches have done something similar, but in that case they used either a contrastive or a language completion objective to find out this. And those are fine. Those capture the semantics well, but they don't really get the visual quality right. So since we want to create images, we should focus on something visual, and we should so they propose a visual reconstruction task for that. So what they do is, I think it is best to be explained by this only. So say we have an image of a clock. We want to explain to the model what a clock looks like. We'll pass it a few prompts, like a photo of a star. So this is a template, a photo of X, and X is the concept you want to learn. So they'll have like 4 or 5 images. They'll for each image they'll pass this prompt. They'll tokenize it. So a photo of, so a tokenizer basically maps each of these tokens into a number. So A goes to 508, photo to 701, off to 73, and S star goes to a special token. And then you have an embedding lookup which maps these tokens to an embedding. So yeah, this is how. So this is most probably a transformer model. So you uh, so given this caption, you tokenize it, and then you get the embeddings for each token. The catch here is we don't know the embedding for S star, so this is something which we want to learn. So this is learnable, and then you pass this through a transformer, and this transformer will finally input a context vector. So it will uh, output a single vector, and it is usually it is like you will pass this to a transformer, and so if this is your transformer, these are your 4 tokens. So you'll get 4 outputs from it in the last layer. For each token you'll get some new vector, then you will take a average of these, and that average would be this context vector. And this context vector represents all the information of the text. And you have your generator. So this is your diffusion model. And you just condition the diffusion model using this context and ask it to reconstruct the input sample. So it is a conditional generative modeling process. So you start from a noisy sample, and if it is unconditioned, then given a noisy sample, it can predict anything. But now, since you're conditioning it on this text embedding, you want it to uh, construct an image which represents this concept. And in this case, you will, so say the generator predicts this image, you will want to have a L2 loss between them. So you'll force the model to uh, predict back the image which represents the concept. So say you have 5 images, you'll condition all of the, so you'll run that, you'll run the conditional generative modeling process. You'll start from noise, you'll predict image, and then you'll do a L2 between the L2 norm between the L2 loss between the input images and the predicted images. And I think they have a L2 loss between each of the noising steps. So in diffusion, you have multiple steps, noising and denoising steps. So I think they also have an L2 norm on the uh, intermediate steps as well. So once you repeat this process enough, also this generator is fixed, this text encoder is fixed. The only thing you're learning is this embedding lookup, this blue part. So what is the embedding of this new token? So this is the only thing which you are learning. Other embeddings are also fixed. As you can see, this lock sign, all other embeddings are fixed. There is only one learnable thing going on here, which is the embedding for this new token. So yeah, that is how it goes. And they use a latent diffusion model in this case, which is, you can use anything I think, but a latent diffusion model is nothing much. So in a normal diffusion model, if you have to predict an image, then say you have an image and you pass it through the diffusion model and you get a slightly denoised image. So if this is a noised image, you might get a denoised image after running it through many steps. But a normal diffusion model runs on the entire image at once. So if this is 64 cross 64, the diffusion model runs on the entire 64 cross 64 image. A latent diffusion model instead works on a latent. So it will work on a vector. So maybe a 128 dimensional vector. And it will gradually denoise it to predict a new vector, which is also 120 dimensional. And then this would be passed through a decoder which was learned before to give this image. So what they usually do is that they first train an autoencoder of some sort, which goes from image to a latent vector, again to an image. So you train this autoencoder, which can map an image to a latent and map a latent back to an image. And you freeze this autoencoder then. And then you learn a diffusion model which denoises a latent. So given a random latent, it denoises it to give a meaningful latent, which can be then passed through this decoder to give you a meaningful image that you want. So this is how latent diffusion models work in a short TLDR summary. You can check out the stable diffusion paper to know more about it. And here they again explain that yeah, we have text embeddings and we replace. So this is just implementation details. And yeah, again, this is the uh, yeah, this is the templates they use, a photo of a star, a rendition of a star. So this is the prompt that they use, and then this is the L2 norm which they have, reconstruction objective. So that is the method on a high level. So now let's look at some of the exa demonstrations of this model. It is a very powerful model. So here they show that given a few images of these different concepts, it can reconstruct that concept in a novel view. So here, given a few images of a teapot, it can generate that teapot in different angles by just a simple prompt, a photo of a star. But what's even more interesting is that since you're learning a concept, you can, and that concept is just a word, you can mix it with other words in natural language to create more personalized creations. So say you provide this new concept, which I think has to do with the texture and the clothing pattern. So if you just say a star sports car, you can get a car which is in that pattern, or a star made of Lego. So you can essentially just use this new concept as a word, as like any other word you would use. So this is pretty crazy. Uh, right. I think this is a bowl. They have learned a particular type of a bowl and they can just say, okay, ramen soup served in that type of bowl, or a photo of a star mask. So a mask in that uh, particular style. So this is pretty cool. You can also do style transfer with it. So you can ask the model to learn the style, like you can use the style instead of like using the object itself. You can just say that I want it to be in the style of a star, and then it will essentially do style transfer. They do say that, note that this differs from traditional style transfer. So we don't wish to maintain the content of some input image. We just want to preserve the style. Then this is concept composition. So you can essentially learn multiple such concepts and combine them. So you can combine the style and the content of two different concepts. So if you consider these two, this style and this clock, so you can say photo of this clock in the style of this style. So you can merge these two, merge multiple concepts together. So they're just like words. So since you can combine multiple words, you can also combine multiple concepts. Also, there are some limitations. So it says that it struggles with the relations between them. So it fails to place two concepts side by side. And they claim that this is because their training objective is a single concept. So yeah, then this is also a very cool use case of bias reduction. So what they say is that since the training data is sometimes biased, so if you just say a stock photo of a doctor, it might be biased towards a particular gender. So what this is that you can use this method to learn a new concept, a new word representing doctor, but in the data set you give, you could have a fairer representation. So you can utilize a smaller curated data set to learn a new fairer word for this concept. So in those 10 or 5 or 10 examples which you will give, you can have a more fair distribution so that this new concept is more fair. So in this case, now if we use SR instead of doctor, you have a much more fairer distribution. So this is pretty cool that you can use this to debias the model in some ways. And they also say that since this star is just another word, then you can use it in downstream models also. So you can like combine it with other models. So in this case, they uh, you consider the blended latent diffusion model in which enables localized text-based editing via mask-based blending. So essentially, uh, you so this is some other model, downstream model, which given an image and a mask, you can like edit that image. So what this says that you can use this new words with other models also. Like if you had a previous model, a stable diffusion model, which had some embeddings and those were used in a downstream model, these new embeddings can also be used as it is with that. So yeah, that is pretty cool. So let's now see how they evaluated the model a bit. So they evaluated not the model, the quality of the latent space embeddings on two fronts, reconstruction and editability. So reconstruction gauges the ability to replicate the target concept. So in this, what they do is that they ask the model to generate 64 images using a simple prompt, a photo of a star, and then they calculate the average clip clip-based cosine similarity between the generated image and the training set of that particular concept. Secondly, they want to evaluate the editability or the ability to modify the concepts using textual prompts. So they generate a bunch of images using these kind of prompts, a photo of a star on the moon and a painting of a star, and then they calculate the cosine similarity with textual prompts without the placeholder. Like an oil painting of a star, you run it through the model, get an image, and calculate the clip similarity with only an oil painting of. So a photo of a star on the moon goes to a photo of on the moon. So they calculate the the clip similarity without the token, so which only captures the modifiers on that concept. So S star represents the concept, and the rest of the things show how that concept is edited or modified. So we want to capture a similarity with the things with the editability of that concept. So they say that here a higher score indicates better editing compatibility and more faithfulness to the prompt itself. So then they use a bunch of methods to like calculate the to evaluate the embeddings by using some techniques from GAN inversion. I can skip these, but I mean, going through them might give some ideas about how latents are being manipulated. So one of them is extended latent space, which essentially maps to describing the concept to multiple learned pseudo words. So instead of having one pseudo word, you have like two or three pseudo words for a particular concept. Progressive extensions is a progressive multi-vector setup. So you first begin training with a single embedding vector, introduce another one after some training steps, and then introduce another one after some more steps. So the idea here is that the network would focus on the core details first and then leverage the other two pseudo words to capture the finer details. Regularization is that so what has been observed before that uh, latent codes which are closer to the training distribution have increased editability. So what they mean is that you have uh, you have a bunch of vocabulary which was bunch of codes which was used during training. If you learn a new code which is near that distribution, then you will be able to edit it more easily. And if it's farther from that distribution, you might not be able to edit it that well. So they use a L2 distance regularizer for enforcing this. Then they also have per image tokens, in which case so in which case rather than optimizing a single word vector across all images, they introduce two things. One is a universal placeholder, which is common for all the input images, and an additional placeholder unique to each image with its own unique embedding. So then you create the sentence in the form of a photo of S star with SI. So where each image is matched to sentences containing its own unique string. And then you jointly optimize with both S star and SI. And the overall hope is that the model would encode the shared information between the given input images, which is the concept in this universal token in the shared codes, and the per image details would be relegated to the per image token. Human captions is that instead of using a special token, what if we have human annotators give a caption to the concept and then use that prompt? So no learning involved, just asking human annotators to give a caption for the concept involved and using that instead of the token. And then textual inversion is their actual method. So what did they observe? First, they observed that the semantic reconstruction quality of the method is comparable to simply sampling random images from training set, which means that the reconstruction ability of their embeddings is same as the reconstruction ability of the training embedding, so which is good. And another thing is that the single word method performs similar as the multi-word method. So basically they are able to capture concepts while using just a single pseudo word. Then they observe that there is a distortion editability trade-off. So embeddings which are closer to the original word distribution, maybe due to regularization, fewer pseudo words, or a lower learning rate, are more easily modified. But they fail to capture the details of the target. And on the contrary, uh, deviating from the word distribution enables better reconstruction but worse editing capabilities. So what they mean there is that suppose you have a training distribution, like all your word embeddings in the training stage occupy this space. If you have a latent new pseudo word which is near this distribution, you are able to edit it easily. because editing comes from the prior knowledge the model has. So uh, how well it mixes with the other concepts that the model knows. That is how editing would work. So uh, like create a painting of a star. That would need the model to understand what a painting is. So that relies on its old information. So if you have a new word embedding which is closer to the original embedding, you can edit it well. But also since you are forcing the new concept to lie close to the original concepts, if the new concept is significantly different from the older concepts, you might not be able to reconstruct it that faithfully. On the other hand, if you go far away from the original distribution, you might be able to capture the details of the concept, but then you might not be able to leverage the existing knowledge of the model that well and edit it that well. So yeah, this is I alluded to this before that I think that this model might not work in learning concepts which are very far away from your training distribution. And anyway, you can't teach it something completely new, which is totally out of domain, because it might not be able to extrapolate because you're not changing the weights of the model. You're not fine tuning it, so you're not giving it any additional knowledge. You're just allowing it to combine the existing knowledge it has. So if all the images it is trained on are cartoonish, you can't expect it to create a realistic image, however hard you try, is what I feel. But these models are trained on very large and diverse data sets, so that is not a problem in practice, usually. And the last observation is that using human descriptions for concepts basically fails. Because humans are like you might give some captions like say here you might give caption like a photo of a statue doing a yoga pose, but it is not really understandable how to give the not that easy to give the exact prompts that would lead to this particular image. So using human captions doesn't really work that well. So what are the limitations of the paper? What they say is that while their method offers increased freedom, it may struggle with learning precise shapes and may instead incorporate the semantic essence of a concept. So when you are teaching a new concept, like the concept of this yoga, or like say the concept of this which one should we take? This bowl, it might, or this teapot, it might learn the semantics of this, like how it is supposed to be, like semantically, but not able to capture the exact precise shapes that this has. It might learn the general concept, but not the exact details. And so they say that for artistic creations, this is often enough, like just learning the concept. And in the future, they will try to have a better control over the reconstruction and stuff. Another problem with that approach is that it is slow, that it has a lengthy optimization time. Learning a single concept requires roughly 2 hours, so that is a lot. Right. They do say that this can be shortened by using an encoder-based approach. So using an encoder to directly map a set of images to their textual embedding, and they say they will explore this in the future. This is basically alluding to the encoder-based approaches, in which case you'll probably take a bunch of images, pass them to the encoder to get the new word embedding directly, like in one shot, in one forward pass. Then they have a social impact work section, which I never really understand the use of. And yeah, that is mostly it. Another limitation which I have talked about multiple times is that since you're not fine-tuning the model itself, it can't learn new concepts, like totally new concepts. So that is something. Overall, I think it was a very cool paper. Like learning how to fine-tune these models to learn your own concepts is something which is very powerful, and people have done a bunch of very cool stuff with this. So yeah, it's great. It is also integrated natively into diffusers. So diffusers, if you open, Oh, not this diffuses. Hugging face diffuses. It is, you can see that it is there in diffusers, and you can like use it to easily do texture inversion on these stable diffusion models and other models. So that is pretty cool. So yeah, that is mostly it for the paper. Thanks for watching.